Hi, Year 12. Welcome back and welcome to the A-level chemistry course. Okay, I'm glad that you guys have all chosen it. At some point, I'd like to ask you all of your motivations for choosing it. Usually, there's quite a lot of people who want to do medicine, and chemistry is actually more beneficial to a medicine course than biology is. Anyway, I'm still interested to hear what everyone has to say. Um, Yeah, welcome back and all that. I'm not going to go into that too much. I'm sure you've heard it from 100 other teachers. But I would like to say that this course is probably a lot more difficult than you've envisaged. Yeah, it's one of the hardest of the A-level subjects to do. And the leap between Edexcel, IGCSE, and A-levels is really quite large. Okay, I couldn't emphasize this enough to my Year 12 students last year, and it probably took them the best part of the first term, if not the whole of the first term, to really kind of get their act together and realize how much work is expected. A lot of it self-guided. You're going to have to be working on your own, not just being, like given stuff all the time by the teacher. You're going to have to go and, actively root things out and read around, do some internet research, but also using textbooks and stuff. So a lot of the onus on the learning is on your back. It's not so much on the teachers as it was in GCSEs. With that said, I think the sooner you realize that, the better it's going to be for you, and it'll be easier throughout the whole of the course. Whereas if you let it go slack in the beginning, then you're going to find it really quite tough towards the middle and the end of the course. Okay, so with that out of the way, let's start on the first topic, okay, which is atomic structure. As you can see from my slide here, it's obviously very fundamental, so it's one of the first topics that we're going to cover. And let's look at these first. Underline the two bullet points there. It's the first and the third one. So we're going to be looking at the knowledge and understanding of the atomic structure and how it's evolved over time, from the Greeks right through to modern times. We'll also look at how an atom consists of a nucleus and the experiment that kind of found that determined that, and that there's protons and neutrons, subatomic particles, and they're surrounded by orbiting electrons. And the electrons are a bit weird. They can be thought of as particles, and sometimes it's more beneficial for us to think of them as waves. So there's a kind of a wave-particle duality, which you'll learn a lot more about if you do physics. Okay, so let's look a little bit more closely at the atomic structure, specifically the electrons and their shells. You learnt in GCSE that the atom was composed of a nucleus and had concentric rings around its shells that held more and more electrons as you got further from the nucleus. Okay, it's actually a little bit more complicated than that. You've actually got subshells within each shell. Okay, so when you look at a periodic table, you're talking about each period as being one different shell, successive shells. Okay, but what we'll see is that there's actually subshells within those shells, and they are either S for sharp, P for principal, D for diffuse, and F for fundamental. Okay, so those subshells give rise to different blocks within the periodic table, and you can see the different color coding here. Okay, this is quite a complex idea to get your head around, but don't worry about it. Just listen to me for a bit, and I'll explain things later on. Okay, so this is the S block. Okay, group 1 and 2. This is the D block, and that's the transition metals. This is the P block. Okay, groups 3 through 8. And the lanthanides and the actinides are the F block. Okay, so that comes about because of these subshells. Okay, within subshells, you've got things called orbitals. Okay, and different subshells can hold different numbers of orbitals. S can only ever hold 1 orbital. P can only ever hold 3 orbitals. D can hold 5 orbitals. And F has 7 orbitals. Okay. Each orbital can only ever hold 2 electrons. They're paired in an orbital. Okay, so that means that in the S shell, where you've got 1 orbital, you must have 2 electrons in that 1 orbital. In the P shell, where you've got 3 orbitals, you've got 6 electrons, 2 per orbital. In the D, you've got 5 times 2, which is 10 electrons, and in the F, you've got 7 times 2, which is 14 electrons. And if you look at the width of all of the groups, the S, I said it had 2 electrons, the width is 2. Okay, the P, I said it had 6 electrons, and the width is 6. The technically, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, so 10 electrons for the D orbitals, and 14 if you count across the lanthanides or the actinides. So yeah, it gets a little bit more complex, and the models of the atom have changed throughout history. Okay, actually, the guy who discovered the electron, a guy called J.J. Thomson, thought that the atom was like a plum pudding, a big blob of positive charge with some negative small charges, kind of particles spread around it. Okay, you've learned about this model in GCSE, which is called the planetary model, which is pretty basic. That came about after Rutherford's experiment, which we'll look at just now. And nowadays, after a guy called Erwin Schrödinger discovered wave functions, we now know a lot more about the actual shapes of where the electrons can exist. Yeah, these dumbbells are like p orbitals or d orbitals or f orbitals, round ones, s orbitals. So we'll look at the shapes a little bit later on. And it's very hard to figure out where an electron is because they're so small and so fast. In fact, sometimes we don't even consider electrons as particles, but as more like a wave. Okay, wave-particle duality is something you learn more about in physics if you do A-level physics. But yeah, it's something to do with the Heisenberg uncertainty principle. If you've seen Breaking Bad, you know he calls himself Heisenberg. Anyway, Heisenberg said that if something's so small and so fast, you can never really know where it is. Okay, so just have a quick look at this question here. How many electrons can the D subshell hold? Okay, so the D has got 5 orbitals in it. And I said before that each orbital holds 2 electrons. So 5 times 2 is 10. Okay, so one D subshell can hold 10 electrons. But that's fairly straightforward. Okay, so the evidence for the planetary model of the atom, which is the one you learnt about in GCSE, came from an experiment performed by a gentleman called Sir Ernest Rutherford at Cambridge in 1910. And what he did is he put some gold foil in front of an alpha particle source. Now, alpha particles, you should know, are helium nuclei. That's just 2 protons and 2 neutrons. So they're positive, right? And he fired these alpha particles at this gold foil. And what he found is that the vast majority of them went through, no problem, but some of them were deflected back, sometimes at really great angles. Okay, now the only thing that could have deflected them back is something also very large compared to the alpha particle, and very positive. Okay, must have been very positive to repel that positive alpha particle back in its tracks, you know, almost 180 degrees in some cases. But because it didn't happen very often, then he realized that, you know, most of the atom was empty space. All those alpha particles were passing through. And if you look at this diagram here, it doesn't explain it too well because actually, you know, the nucleus would be tiny, like almost invisible. It's so small compared to the size of the overall atom. That's why the vast majority of the alpha particles could pass through. But if they hit the nucleus, then they would be turned back or deflected sometimes if they went near it. Okay, so pretty smart experiment and good thinking, you know, to look at the results. And, you know, it was a really boring experiment. Apparently his students used to have to sit around this deflector here, this detector around here, and wait for one of these particles to flash as it hit the detector. Okay, and that might take like hours or days. So really quite a boring experiment. But yeah, I mean, he had the perseverance to collect the results and interpret them. Okay, so yeah, I've already answered that question for you. What particles are in a helium nucleus? Okay, it's just 2 protons and 2 neutrons. Okay, now I want you guys, in your own time there, well, during this lesson ideally, to go through this experiment here. So have a play around with it. There's a few different things you can change. It's a simulation online, and you can change a few variables, okay? Just try and move sliders and change arrows and all that kind of stuff, and you should be able to see the effects and simulate exactly what Rutherford did in his alpha particle scattering experiment. And after that, I've got a couple of videos I want you to watch. Okay, you can watch them in your own time. And that brings us to the next bullet point, which is this one here. Just turn on my laser pointer again. Protons, neutrons, electrons, their relative charge and relative mass, okay, which is really a revision of what you've already learned in GCSE. You must have seen a table similar to this in GCSEs. You need to know their relative charges, the relative mass. Remember, an electron is very light, almost 1/2000th the weight of a proton or a neutron. And their symbols. Yeah, pretty straightforward. Usually the electron has a negative charge on it. Okay. So the element shown in the diagram must be, anybody? Helium. Okay, 2 protons, 2 neutrons, 2 electrons. Let's look a little bit closer at relative atomic mass, okay? And as you know, we can't deal with kilograms because they're just way too big relative to the mass of nucleons, you know, things like protons and electrons and neutrons. So when we talk about a nucleon, that's something in the nucleus, yeah, either a proton or a neutron. It has an atomic mass of 1, which is called an AMU, atomic mass unit. Okay, now the funny thing is that not all protons and neutrons weigh the same. Okay, if they're in very large atoms, they tend to have a slightly lower mass, and that's because specifically neutrons are used to glue together the positive protons. The positive protons in the nucleus are going to obviously repel each other and trying to get away from one another. So as atoms get bigger and bigger and you've got more and more positive charge in the center, then the neutrons, more of them are needed to kind of bind it together. And that's because as the neutrons kind of fuse the nuclei together, they lose a little bit of mass. Some of their mass is converted to energy to hold together the protons that are trying to repel each other. So this loss of mass is known as the mass defect. Okay, so yeah, take it for granted that nucleons have different masses depending on which atom they're in. So carbon has to be taken as a standard, okay? And what we say is that 1/12 the mass of carbon, because it has 12 nucleons, 6 protons and 6 neutrons in its most common isotope, that's carbon-12. If we divide that by 12, then we're going to end up with the official value of what an atomic mass unit is. Okay, so it's a standard, it's carbon. And the reason it was chosen is because it's relatively stable. Okay, it's relatively available, especially as graphite. Okay, it's very cheap as well as graphite. Easily transported. Okay, it's not flammable or poisonous or a gas that needs to be pressurized, and it's also important to life. Obviously, the early scientists attributed some special kind of quality to carbon because it's the basis of life. Why do you think hydrogen wasn't chosen? Well, hydrogen's a gas, yeah, and it's flammable. It's not very stable. It's not going to be easily transported because it's a gas. It needs to be pressurized, and it just doesn't have. It's not that easy to obtain either. You have to electrolyze water to get it. So yeah, hydrogen's been known for a lot less longer than carbon. And it doesn't have that importance to life that carbon does. Okay, so looking a little bit deeper, and this is not really something you need to know for your course, okay? But it's just out of interest. Okay, if you look a little bit closer, the nucleus and the protons and the neutrons in it, they're actually made up of quarks. Okay, and there's different types of quarks, and they're held together with what's known as gluons. Okay, so these even smaller subatomic particles are discovered using particle accelerators, like at CERN, yeah, under the Swiss Alps, and also the LHC, which is, I think, somewhere in America, perhaps Boston. The Large Hadron Collider. What they do is they spin around nuclei and atoms and smash them into each other. They circle them in a really, really fast circuit and get them up to speeds approaching the speed of light, and then they smash them into each other, and then they see what little particles come off. But it's not required for your syllabus, it's just out of interest. Okay, so here's the whole family that they've discovered or claimed to have discovered so far. And you can see there's a whole bunch of quarks here. There's all these neutrinos, electrons, muons, taus, bosons. You know what a photon is? That's to do with light. P1s hold together the quarks. And you've got these weird things, Higgs bosons, gravitons, dark matter, tachyons, and the good old protons and neutrons and the nucleons. These are theoreticals, the green ones, yeah? So the big Higgs boson is the one that we're trying to discover recently, well, about a couple of years ago. And they reckon that it is the particle that imbues everything with mass, gives things mass, but they still haven't, confirmed its existence. Okay, so for homework, I'd like you to do these two bits of work for me, two activities. The first one is just a keywords crossword that I created myself, and the answers are down here. The second one is a chem sheets worksheet, all about atomic structure and stuff that you just covered. And again, the answers are down there. Shouldn't take you too long. Yeah, you're going to find that the workload for homework is also going to be a bit more than it was in GCSEs. So yeah, let me know if you have any problems accessing those files. You should be able to just open this PowerPoint and then click on the links. Okay. All right, all the best.